Today I am going to discuss trial questions from KMKP year 2022 and 2023. Let's look into the questions. A line with a wavelength of 486.4 nanometer was observed in the Balmer series of this emission spectrum of hydrogen. Okay, let's highlight the information given in the questions. The question gave us the wavelength, which is 486.4 nanometer. And then from the question, we can know that the line is in the Balmer series. Okay. Determine the initial and final values of the energy level associated with this emission. To answer this question, we must use this formula. Before we substitute all the values into the formula, one of the tips I'm going to share is list down all the important details that we can find from the questions. Here I have listed down all the information we can get from the questions. The question gave us the wavelength, but the question gave the wavelength in nanometer. In the formula, we cannot substitute the value in nanometer. Instead, we have to change the value to meter first before substitute the value. And then the line is in Balmer series, so the final value will always be 2. Why it is specifically N1, not N2? Because N1 should always less than N2. Remember that. And then in the formula, we have to substitute the RH value. What is RH value? RH value is a Rydberg constant. We have a constant value for this. So for this question, we have to substitute 1.097 times 10 to the power of 7 meter negative 1. Let's substitute all the values into the formula. Okay, after substitute the values, we can get n equals to 4. So the question asks us to determine the initial and final values, right? So we have to write again, initial value is 4 and final value is 2. Let's move on to the next question. State the region of electromagnetic spectrum in which the line is formed. We can know that the line is in Balmer series. We have totally 5 series, which is Lyman, Balmer, Paschen, Brackett and P1. For Lyman, the region is ultraviolet. For Balmer is visible, and for the other 3 series, which is Paschen, Brackett and P1, the region is infrared. From this info, we can get that the Balmer series, the region for Balmer series is visible. Next question. Determine whether the following set of quantum number are acceptable or not. Okay, the sets of quantum number that are given is n equals to 3, l equals to 1, m equals to negative 1, s equals to plus 2. So we have to see one by one. N is principal quantum number. The possible number is start from 1, 2, 3 and so on. For angular momentum quantum number, the possible number is 0, 1 and so on. Here I have given the notes for angular momentum quantum number. The possible values start from 0, 1, 2, 3, 4. Usually we will use until 2, until subshell D. For subshell F and G is not common. Okay, for M is magnetic quantum number, and then the possible value is depend on the angular momentum quantum number. If angular momentum quantum number starts with 1, and then the M will be negative 1, 0 and positive 1. And then S represent electron spin quantum number. For S, we have only 2 values, which is positive half and negative half. These are the 2 values we can write for electron spin quantum number. So, can obviously see that the value given for electron spin quantum number, which is plus 2, is definitely wrong. So, the answer will be not acceptable. Another set, they gave n equals to 2, l equals to negative 1, m equals to plus 1, s equals to negative half. As I said, possible values for principal quantum number is start from 0, 1 and so on. And then for angular momentum quantum number, the possible values start from 0, 1, 2 and so on. Here we can find that the value given is not acceptable, but it's okay. We see other values first. For magnetic quantum number, the value given is positive 1, which is acceptable. And then for electron spin quantum number, the value is negative half. As I said, we have only two values, which is positive half or negative half. Since they gave negative half, the value is acceptable. So we can see that the value given for angular momentum quantum number is not acceptable. So the answer will be not acceptable. Let's move on to the next question. State of Power principle. The answer for this question is Aufbau principle states that electron fill the lowest energy orbital first and other orbitals in order of ascending energy. So that means the electron fill the lowest energy orbital first to I energy orbital. So the lowest energy orbital will be 1s. The proton number of copper is 29. This is the information given in the question. Write the expected and actual electronic configuration of copper atom. Explain its anomaly. Give a set of quantum numbers for the valence electron that occupy the s orbital of copper. So the question is long a bit, so I suggest to highlight what the question wants us to answer. First, I highlight write the expected electronic configuration. This will be your first question. The second question will be write the actual electronic configuration. Then the third question is explain its anomaly. And then fourth will be give a set of quantum numbers for the valence electron. Okay, note that they ask for the valence electron that occupy the s orbital. Okay, let's answer for this question. The expected electronic configuration, we have to fill the lowest energy orbital first, as I said. So the lowest energy orbital will be 1s. So we will fill the electron one by one. For s orbital, we can fit into 2 electron. For p, we can fit until 6 electron, and for d, we can fill until 10 electrons. So we write it one by one. The electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d9. This electronic configuration follows Aufbau principle. Why I say that? Because in the first question, we can see the Aufbau principle states that electron fill the lowest energy orbital first. So we using Aufbau principle, we fill the electron from low to high energy orbital. Let's see the actual electronic configuration. The actual electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d10. We can see we removed one electron from the 4s orbital, and then from 3d orbital we add one electron. In the expected electronic configuration, we saw that 3d orbital have only 9 electrons, right? Now in the actual electronic configuration, the 3d orbital have 10 electrons. Why? Because we move one electron from 4s orbital to 3d orbital. As I said, 3d orbital can fit into 10 electrons. Since in the expected electronic configuration, the d orbital has 9 electrons and need only one electron to complete its orbital. So we moved one electron from the 4s orbital, and then the electron filled into the 3d orbital. This is what you are going to explain for the third question. The third question is explain its anomaly. An electron from 4s orbital is moved to 3d orbitals to achieve the extra stability of fully filled 3d orbital. Fully filled 3d orbital is more stable than partially filled 3d orbital. Okay, now I'm going to highlight the main key point that you should add into your answer. An electron from 4s orbital is moved to 3d orbital. This is one key point. Another key point is achieve the extra stability. This will be your second key point. And then third key point will be fully filled 3d orbital. Fully filled 3d orbital is more stable than partially filled 3d orbital. is the difference between fully filled 3D orbital and partially filled 3D orbital? Partially filled 3D orbital is what we saw in the expected electronic configuration, which is 3D9. 3D9 is considered partially filled 3D orbital because it is not half filled and it's not fully filled. Fully filled means the orbital fit into 10 electrons, and half filled means 3D orbitals contain 5 electrons. That is called half filled. Okay, next, the last question, they asked to give a set of quantum number for the valence electron. What is valence electron? Valence electron is 4s1 and 3d10. This will be the valence electron. But the question specifically asks for the s orbital. So we will see the for s1 only. So the set will be 4, 0, 0 plus half, or you can write 4, 0, 0, negative half. Why is it 0? Because in the previous question, I got mentioned that for s orbital, the angular momentum quantum number is 0. If the angular momentum quantum number is 0, then the magnetic quantum number also will be 0. That's all. I hope you all could learn something from this video. Thank you for watching.